hit record. Should be okay. So hello. So today's speaker is Professor Kathryn Zurek. So we are very happy to have her here. So Professor Zurek obtained a PhD at the University of Washington, focusing on neutrinos, astrophysics, and cosmology. She held position at the University of Wisconsin-Madison and then the David Schramm Fellowship at the fellow at Fermi National Accelerator Laboratory, Fermilab. And during this time, she focused on developing concrete model of hidden sector dark matter. In 2009, sorry, she became an assistant professor and then in 2012 an associate professor at the University of Michigan, where she developed these theories in the context of anomalies from the direct detection experiment. 2014, she moved to Berkeley, where she focused on proposing new ideas to detect light dark matter, and since 2019, she is professor of theoretical physics at Caltech. And today she will present new ideas in dark matter detection. So I'll leave you the stage. And thank you very much. And I will stop my video.
All right. So thanks for the invitation to give one of these talks. It's always a bit of a trade-off between the ease of not traveling and the disadvantages of not being able to communicate one-on-one. So I'm going to give a very broad overview today about a number of the ideas that I've been working on, new ideas in dark matter detection. And before we dive into talking about, the particle physics, it's just a good reminder that we have this beautiful paradigm that's been assembled from the time that the universe is a second old through CMB measurements, large-scale structure, supernovae, galactic rotation curves that all together give this consistent picture. And whenever I'm asked about, why not modified gravity, or is the dark matter paradigm going to go away? I think it's good to remember that, we really have no alternatives that explain all of the observations that we see. But of course, it relies, all these measurements on very large scales in the universe rely on the fact that gravity is coherent on cosmological scales. And that's to say that gravity, of course, there's no shielding effects. Gravity is just proportional to the mass of the objects that are interacting. So, when you look at two clusters of galaxies colliding with each other and their gas is getting stripped off, can you see my cursor here? Probably not. Here you can see my cursor. Here or here? Can you see my cursor?
I saw the cursor in the black on the pictures.
Okay, now you can see it?
I cannot.
Okay, so now you can see it.
Yes.
Okay, so that's a reminder. I need to point on the other screen. Okay, so this gravitational coherence, the fact that you have these two clusters of galaxies, for example, passing through each other, the dark matter in them is barely disturbed, and yet the gas here is stripped off. So this helps us learn about the aggregate properties of dark matter, but of course what we'd like is a theory. We'd like to be able to reconstruct Lagrangians, the forces, the associated forces. And so in order to do that, at least up to this point, we have to assume that dark matter has some form of interactions that are other than gravitational. So, so that sometimes can feel a bit overwhelming, the breadth of the possibilities, because in fact, dark matter can be as light as 10 to the minus 23 eV, or if it's in the form of compact objects, as heavy as 1,000 solar mass, consistent with either the de Broglie wavelength of a particle being on the order of the galaxy, our galaxy, the Milky Way galaxy, or the fact that we observe dark matter to be smooth on large scales. And that limits it to be lighter than 1,000 solar mass. So if we convert solar mass to particle physics units, then that which is 10 to the 57 GeV, we can see that we have some you know, 80 orders of magnitude here in dark matter mass, actually 90 orders of magnitude. And so we've been focused just on this narrow window around 100 GeV for the WIMP paradigm. And that was a good place to start looking. Okay. And that was a good place to start looking. And the reason is that the weak forces have the right scale for detection, for abundance, and for cosmology. So the weak interaction cross-section here, if we just write down parametrically, the weak interaction cross-section goes like this: coupling constant to the 4th power, the reduced mass between the dark matter and whatever other particle it's interacting with, and then there's a Z boson mass to the 4th power. So if you just put in a common mass for the dark matter and for the Z boson around 100 GeV, that cross-section turns out to be about 10 to the minus 34 centimeters squared. So now if you further, let me just skip ahead here. If you further say that the annihilation rate goes like that weak interaction cross-section times a relative velocity at freeze out, which is going to just parametrically be set by the speed of light, then that comes out to be about 10 to the minus 24 centimeter cubed per second if you put in the scale of 100 GeV. So we know that if dark matter annihilates to the standard model, this is the weak freeze-out paradigm, which I'm sure you're familiar with, that we get the observed abundance of dark matter if that annihilation cross-section is on the order of 10 to the minus 26 centimeter cubed per second. So that very naturally points us to the weak scale, or actually somewhat above the weak scale, around 2 TeV is where one naturally gets the observed abundance of dark matter if its abundance is set by interactions with standard model forces. And so as a result, looking at dark matter in this very narrow window across the entire range, which is motivated or consistent astrophysically, is still a good place to start looking because of this fact. However, this WIMP paradigm does have other implications. One of them is that the interaction cross-sections are just too small to have any relevant impacts on structure formation. So to state it another way, WIMP dark matter from a cosmological point of view is very boring because it freezes out, the abundance is set in the very early universe, and then not much happens afterwards. And that's true even in the universe today. So to be able to see dark matter self-interactions, for example, when two galaxies collide with each other, the interaction cross-section would have to be about 10 to the minus 24 centimeters squared per GeV. And that's about 10 or more 8 orders of magnitude larger than what would be predicted for WIMP scale dark matter. So from that point of view, the only types of signatures that you might expect wouldn't be seen then cosmologically. On the other hand, that interaction cross-section of 10 to the minus 35 to 39 centimeters squared is really large for direct detection experiments. So as you know, because you're at Snow Lab, the center of where many of these experiments are happening, these direct detection experiments look for interaction cross-sections that now, with the current generation of experiments, Xenon 1 ton or LZ, which will come online in a couple of years, are now into the 10 to the minus 46 centimeters squared interaction cross-section. And when Xenon N ton, starts, will be on the same order as the LZ experiment, pushing down towards this neutrino background. So strictly speaking, the WIMP interacting with the weak forces in the standard model, which would be all the way up here at 10 to the minus 39 centimeters squared, or even a little bit larger, is ruled out by many orders of magnitude in cross-section. So what we're really doing right now is reaching for this window where dark matter interacts with the standard model via the Higgs boson, and that's this orange area here. So, so this window here, right around 100 GeV, is well motivated from the point of view of its abundance from the cosmology, which is just cold dark matter, and from the fact that you can search for it in direct detection experiments. If you look above this WIMP window, so at greater than 10 TeV, studying the relic abundance through the interactions with the standard model is challenging. And the reason for that, again, looking at this interaction cross-section, is that as this mass scale goes up, the annihilation rate goes down. And pretty rapidly, this annihilation cross-section, even for coupling constants, which are order 4 pi, simply becomes too small to explain the observed relic abundance. And so for heavier dark matter, its abundance does not typically motivate interactions with the standard model. Okay. At even heavier masses, again, you generally wouldn't motivate the relic abundance through interactions with the standard model. On the other hand, these very heavy dark matter particles can become heavy enough that you can take advantage again of this gravitational coherence. So I want to give you one example of that before I move on to talking about direct detection. Above 10 to the minus 13 solar mass, which is very heavy for particle dark matter, but quite light for astrophysical structure, pulsar timing can be effective. So let me explain briefly what pulsar timing is and how it could detect dark matter substructure. So you have a telescope here on Earth, obviously much more sophisticated than the one shown here. You have a distant, not very distant pulsar, so it's subgalactic scale. So in our galactic neighborhood, say on the order of a kiloparsec away, we're about 8 kiloparsecs from the galactic center. And pulsars are very accurate clocks, by which I mean that if you measure the time at which a pulse appears from one of these millisecond pulsars, and you time that over the scale of decades, you can fit the time of arrival very well with just a quadratic function. So one that depends on the period, is extremely stable, and typically these have very small spin down of their periods, which is calibrated in terms of mu dot. So what can happen is a dark matter subhalo can come by, and it can cause either the pulsar or the Earth to accelerate, or it can cause a Shapiro effect along the line of sight from the pulsar to the Earth. And that gives rise to a shift in the time of arrival of a pulse from this pulsar. And so as a result, you can now ask the question, if I observe these pulsars over the time scale of decades, which in fact they do with instruments like, for example, nanograv is one such pulsar timing array, and in the future, the square kilometer array will be able to do these kinds of measurements. What you find is that you can have sensitivity to dark matter substructure. So this is a fraction of the dark matter, okay, in some substructure of mass m. So if this drops below 1, you're able to constrain such dark matter substructure. And you can see that for different density of dark matter substructure, so concentration parameter tells you about how dense it is, you're able to actually observe such dark matter substructures. So that's a very interesting subject, not one I'm going to talk about today because of this audience, but if dark matter, the takeaway I want you to get is that if dark matter is heavy enough, there are very sensitive gravitational redshift effects that you can look for in these timing measurements. So that's at the very high end. On the very low end, where dark matter has a very low mass, it has a relatively large de Broglie wavelength, dark matter behaves like a wave. rather than an individual particle. So the dividing line between particle dark matter and wave-like dark matter is when the dark matter is about an electron volt. So what you're doing there is comparing the momentum of the dark matter, which is set by, the mass times the virial velocity of the Milky Way for making observations in the Milky Way, where that becomes larger than the typical interparticle spacing. And so in this case, you don't want different detection techniques come into play. So rather than looking for individual particles as you do in a WIMP-like experiment, you want to use some type of detection technique that takes advantage of the wave-like nature of the dark matter. So this is the famous example, of course, of this is axion dark matter, where you would use cavities or some other AMO type techniques that can really capitalize on this wave-like behavior. We're not going to spend, that's also a very interesting subject. We're not going to spend time talking about that. Instead, we're going to focus on this intermediate regime where the observation via particle interactions with the standard model is still highly motivated and it's not detectable with traditional WIMP experiments. And these hidden sectors arise very generically in top-down constructions. So again, going back to this simple back of the envelope estimate, if you take the interaction cross-section, just some alpha self-coupling constant squared over the mass squared, you can lower the mass and the annihilation cross-section is plenty large to set the relic abundance that we observe in our universe today. So you're not running up against this so-called unitarity problem for dark matter abundance. And in addition, these scattering cross-sections in some cases can become quite large. So this dark sector dynamics are now complex and astrophysically relevant. They can change, in some cases, the structures of galaxies, clusters of galaxies, dwarf galaxies. And so in principle, you can look for signatures of these dark sectors in the sky. That again is another interesting discussion. For this audience, I'm going to focus on direct detection. So I've said that as the dark matter mass drops below the weak scale, which is motivated to set its relic abundance via interactions with the standard model, you can still set the relic abundance through interactions with the standard model at these lower mass scales. However, the direct detection experiments, at least until about 5 years ago, 5 to 10 years ago, really had no sensitivity to dark matter with mass below about a GeV. And that was simply because this threshold here is set by a combination of how heavy the target nucleus is and the fact that the typical energy resolution, the energy threshold in these experiments is on the order of the KeV scale. So what we want to know is what kinds of ideas do you need in order to look for much lighter dark matter. And by now, there have been a range of ideas that have been proposed, some that are being implemented right now and some that are more futuristic, to go from the 100 GeV scale, this is where the traditional WIMP experiments live, KeV energy resolution, down another 3 orders of magnitude in mass, where you need electron volt energy resolution. This is really where I would say the front lines are right now, using either semiconductors or ionization. And in scattering, that will allow you to get down to MeV mass. Then to go the next 3 orders of magnitude down to KeV mass scale, you need new types of systems, slightly more exotic types of systems, and also 3 orders of magnitude better energy resolution. And so I'll focus most of the discussion here. That's where I've been working. And then also I want to leave you with the fact that for every order of magnitude that you get up here in dark matter mass through a scattering process, you get another order of magnitude down here through an absorption of the particle dark matter's rest mass energy. So when you combine all these techniques together, you'll be able to get about 12 orders of magnitude in dark matter mass if eventually you're able to get milli-eV energy resolution. So where we're currently at is, you know, CDMS, semiconductor-based experiments, like some types of the CDMS, you know, HBEV, for example. They also have some zero field work that's going on, mostly through Matt Pyle's lab. And also there is Sensei and DOMIC that are pushing down to this electron volt energy resolution, currently with background issues that they're trying to solve. Okay, so this is where we're at with current experiments. And then we're going to push down another couple of orders of magnitude, probably to a couple hundred milli-eV. And I'll talk about the kinds of physics that you can get once you get there. And then ultimately, where you're getting down to the milli-eV energy resolution. Now, as I've said before, these light dark matter candidates are motivated to couple to the standard model through their relic abundance. And this part of it is similar to the WIMP, but the mechanisms that sets the relic abundance is different than the WIMP. So the two most popular examples, simplest examples that give rise to detectable cross-sections in direct detection experiments are a process known as freezing and then asymmetric dark matter. So to just state this very simply, you can produce dark matter through a rare E plus E minus annihilation process to produce dark matter. Dark matter does not become thermalized with the standard model. It in fact has very feeble interactions with the standard model, but the same process that produces the dark matter will also allow for a scattering process. So on these plots, you'll see this orange band. Now these plots go all the way down to KeV mass dark matter. And then there's this interaction cross-section now with the electrons. And what you'll see is reach curves. I'll always project for kilogram year exposures. So these are small experiments by the scale of WIMP experiments, but still quite a bit larger than what where the experiments kind of gram scale experiment or even milligram scale experiment, which are Sensei, for example, is a gram scale experiment by now, and still with backgrounds, but nevertheless you can just directly scale these reach curves up, and you can see that for kilogram year type sensitivity, you'll be able to reach freezing by many orders of magnitude. The other example is asymmetric dark matter, and the idea there is that it's the particle-antiparticle asymmetry that sets the relic abundance. And so you need to have a minimum annihilation cross-section of chi-chi bar goes to E plus E minus in order to have an asymmetric dark matter candidate. And so for dark matter masses above an MeV, this actually produces quite large scattering cross-sections that are not very much below the current reach of experiments. So that candidate, that particular model, will be covered, I think, in the relatively near future. So one thing that I get asked about fairly frequently, and I'd like to comment about it here, is the complementarity between direct detection experiments and accelerator probes. So accelerator probes do not have good sensitivity to these light dark matter particles. They just don't. So for example, the LHC, even a number of high intensity experiments won't have sensitivity to these light dark matter particles. And the reason at just the very basic level is that high energy accelerators probe particles with a high mass, a mass which is at the center of mass energy of the collider, that have large couplings to the standard model. And when I say large, I mean 10 to the minus 2 or larger. Direct detection experiments, by contrast, are intensity experiments. They're even more intense than accelerator intensity experiments. They probe light mediators with extremely small couplings to the standard model. So for example, this freezing curve features a coupling of this mediating particle to the electron, which is 10 to the minus 10. It's a very small number. No accelerator is going to be able to reach that. This is a unique domain for direct detection experiments. So before I go further, let me talk a bit about kinematics, because it explains in a very simple way the dominant drivers for direct detection experiments. So as you all know, the WIMP experiments are based on elastic scattering. Dark matter comes in, it sees a target nucleus, there's an elastic interaction process. You can compute the non-relativistic scattering, momentum, and energy deposition. The energy deposition is just the momentum transfer squared over twice the nucleus mass. Of course, the maximum amount of momentum you can transfer is just twice the momentum that the dark matter carries. And you can see that what happens is the dark matter drops below nucleus mass. So if you take a heavy nucleus like xenon, that mass is around the weak scale. So one of the reasons why nuclear recoil was a good experiment to do for WIMP dark matter is because standard model nuclei have masses that are around the weak scale. If you're looking for light dark matter, you can just immediately see, based on the simplest argument, that if the dark matter is much lighter than the target nucleus mass, nuclear recoil experiments are not a very good way to look for such light dark matter, because you extract a very small fraction of the kinetic energy that dark matter is carrying. So the simplest thing that you can do to extend the reach is just to look at a lighter target. So rather than having a very heavy wall, instead you make it a somewhat lighter wall, an electron. And so this, in fact, was the first ideas that people looked at back in 2012, was to look at the electrons in an insulator like xenon, in which case, in order to get a signal, you have to ionize that electron, deposit around 10 electron volts of energy. And in semiconductors, you need to promote an electron from the valence to conduction band. That costs you in the ballpark of an electron volt. And that sets the minimum dark matter mass that you have sensitivity to. So with ionization energies on the scale of 10 electron volts, it means you have sensitivity to dark matter at 10 MeV or heavier. And likewise, for semiconductors, it's 1 MeV or heavier. So now, as I said, I wanted to focus on the question of, how is it that I go the next, 3 to 4 orders of magnitude in mass? These experiments now are moving forward, as I said, with, HBEV and super CDMS, with a zero field version of that, with Sensei and DOMIC are both moving forward. There are some efforts within Xenon. All these efforts are moving forward to look at dark matter as light as an MeV. But what happens once the dark matter drops below an MeV is that its de Broglie wavelength becomes longer than the interparticle spacing in typical materials. So in that case, the degrees, your lattice degrees of freedom, the degrees of freedom from an effective theory point of view that are relevant to look at, are collective excitations. And collective excitations are phonon modes or spin waves. So these are very common modes in materials. And as a result, these principles that I'm going to describe, which work very well for polar materials, for example, can really be applied to just about any material. And I'm going to explain to you what are the coarse-grained properties that one is looking for in a material to have strong sensitivity to light dark matter. And so what I and my group have been doing the last several years is to, so this is the principle. Of course, what what I did at first was to think about specific examples and then generalize to the principle. So the first idea thought about was superfluid helium, but then I found that there are in fact much nicer materials. And in fact, the conclusion from this investigation was that polar materials seem to have the best properties to couple strongly to a wide range of dark matter candidates. Now, this is at a very high level. There are lots of details that go into these calculations. Broadly speaking, it depends on the nature of the collective modes in the target material and the nature of the dark matter couplings to the target. So let me be specific and focus on this last case where dark matter interacts very strongly with this material. And that is the case of polar materials. So let's take a simple polar material, gallium arsenide. It features 2 ions in a unit cell. And so there are 2 possible types of oscillations that can occur in this material. So either where the ions oscillate in phase, and there are of course 3 directions in which you can oscillate in phase. These are acoustic modes. There are always 3 acoustic modes in any material, and those have gapless dispersion. So at 0 momentum transfer, those modes don't carry any energy. So there are 2 longitudinal acoustic, sorry, two transverse acoustic and 1 longitudinal acoustic mode. And they are characterized by the speed of sound, which sets the slope of this line. So higher speed of sound corresponds to a higher energy for a given momentum transfer. The other kind of mode that generically appears in materials is where the ions are oscillating in some way out of phase. So optical materials, those ions are oscillating out of phase, and those, because of the symmetry properties of the materials, have gapped dispersions. So at 0 momentum transfer, they have a finite energy associated with those modes. So now that's the spectrum of the modes. Now this is a very simple material that you can actually do with a pretty simple Hamiltonian analytic calculations for the dark matter excitation rates in these materials. Materials get much more complicated than that. So one example that is particularly nice, also because it's already been used in direct detection experiments, and that's sapphire, Al2O3. So there are actually 2 of these Al2O3 compounds in a single unit cell, so 10 ions in a single unit cell. And that means that there are actually 30 of these modes. 3 of them, again, are the gapless acoustic modes, and the remaining 27 are gapped. Not all of them will couple to dark matter, but a number of these modes will, depending on the selection rules for the process. But these gapped modes in particular, actually, because they oscillate out of phase, set up oscillating dipoles. And that oscillating dipole, you can couple dark matter to quite nicely. The other feature of this is the kinematics. So I said that nuclei were poor kinematic match to dark matter because of the fact that if I ram a dark matter particle into a very heavy target nucleus, it deposits a very small fraction of its energy. Here, however, you actually have these, let's call it inelastic modes. These optical modes, which have a finite energy at 0 momentum transfer, they're inelastic modes. And so as a result, it's possible to have a better kinematic match with these modes. So the easiest way to try to work this out at kind of a qualitative level is just to observe that the deposited energy goes like the dark matter velocity times its momentum transfer. And the dispersion of the modes in the material, if I'm looking at an acoustic mode, goes like the speed of sound times the momentum. Now, typical speed of sound in materials, depends, of course, on the material. But, you know, if you're looking at, say, silicon or germanium, speed of sound is on the order of 10 to the minus 5 times c. And that's about 100 times smaller than the dark matter velocity in our galaxy. And as a result, dark matter in general will not couple very well to these modes. Now you get a better coupling if you have a harder material with a higher speed of sound. But in general, you actually prefer to couple kinematically to these gapped optical modes. Now I should also mention that even though these modes, I call them optical along with condensed matter convention, optical does not always mean that they have a strong coupling to photons. So for example, silicon is a material that also has these gapped phonons. They're optical phonons because they are gapped, but they don't couple. Silicon is not a polar material, so they don't couple strongly to the photon. Nevertheless, if you couple, for example, to nucleon number, and you can move those ions around by a scalar coupling, you can still excite those modes. But polar materials are particularly nice because if I have a dark photon mediating the interaction, and I have this strong oscillating dipole, I can actually set up a very strong resonance between the dark matter and those optical modes. There's one other feature of polar materials that makes them particularly nice for dark matter detection, and that's that you naturally get directionality. So for WIMP experiments, you know, almost the holy grail of direct detection has been looking for directionality in dark matter detection because it's the smoking gun signature for dark matter. These materials have it naturally. So you can imagine if I take one of these polar materials, so this one is sapphire, and I set up one of these oscillating modes, so this is one of the optical modes, you can imagine that the strength of the response that is induced in the material can depend on which direction the dark matter particle comes in and excites that response in the material. So this is a generic feature of all polar materials because the structure in these materials is never fully isotropic. However, if you look at a material like gallium arsenide, it's actually quite isotropic. But in a material like sapphire, you can have fairly strong anisotropies in the material. And so as a result, as the Earth rotates on its axis, the detector, which is sitting on the surface of the Earth, has its orientation with respect to the dark matter wind, which points towards Cygnus, change as a function of the time of the day. And that induces a modulation as a function of the time of day. And that modulation, in some cases, here's for sapphire, depending on the dark matter mass, this is looking at 50 keV dark matter, actually induces a modulation which is order 1. So this will be very powerful if you have a signal for being able to show definitively that such a signal would be coming from dark matter. It's a smoking gun signature. So I've tried to establish here that polar materials are a very powerful probe of light dark matter. But of course, if you're going to go and build an experiment, you'd like to know what exactly you should build the material, you should build your target material from. So we did with a couple of condensed matter friends, they did a high throughput material search, and we utilized our framework to compute the dark matter interactions rate. And then here we have the interaction cross-section reach, again for a kilogram year exposure as a function of the dark matter mass. And here are the range of target materials. So we actually considered about 25 materials. And so here, you know, for the sake of legibility, we just pulled out some of the most desirable. you can see that one of the real winners that we found was silicon oxide, which has an extremely strong oscillating dipole. It does even better than sapphire, especially at the low mass N. Calcium tungstenate is another one that does quite well. And the nice thing of some of these materials is that they'll have a fairly large daily modulation. We're just finishing up a work. My student is doing some work right now on comparing also the modulation reach for these target materials. So in the interest of time, I'm going to skip the next 2 slides on superfluid helium, for which you need a multi-phonon process, and move on to a material now, a different type of material, a very different type of material, where rather than exciting phonons, which are collective modes of ion oscillations, where instead you're doing electronic excitation. Now, you're probably familiar of electronic excitation in semiconductors, where you have a band gap on the order of an electron volt. So let's suppose that we want to find a material that has a smaller gap so that we can look at light or dark matter. So one material, actually the first material that I considered early on, was a superconducting material. And that seemed like it was a desirable target because it has a high density of electrons, and those electrons, when they're in the superconducting phase, have a small gap on the order of a milli-electron volt. And so it seemed like these materials could be highly sensitive to light-dark matter. However, there is a catch. And that catch has to do with the fact that in materials that have a high density of electrons with a small gap, they also have a large polarization tensor. That polarization tensor characterizes the in-medium optical response. So if I write this down as an effective coupling of the dark matter through this dark photon, A prime, which kinetically mixes with the photon to couple to the electromagnetic current, the effective coupling of the dark matter to the electromagnetic current is actually suppressed by the optical response of the material. And you can show this from first principles. So there are a lot of details hiding in this polarization tensor, but suffice it to say that metals, as you would expect, have a very strong optical response. And so when you compute as a general function of the momentum and energy transfer, you find that they have a weak coupling to dark photons. So this, as a matter of practice, destroys the reach to light-dark matter. However, materials can be quantum engineered. This, in fact, is what condensed matter theorists do. The tool that they use to do this is called density functional theory. And so what they're able to do is to take a material, let's say it's a semiconducting material, type material, they can actually engineer the structure of the bands. So for example, instead of having, in an ordinary metal, this giant Fermi surface, you can have something which is still called a semimetal. And the reason why it's called a semimetal is because it has a small gap for the electrons, but its band structure is actually more similar to a semiconducting band structure. So the overall structure, band structure, is that far away from the Fermi level, the band structure looks very similar to a semiconductor, but near the Dirac cone, this point where the bands cross the Fermi level, then you can get an excitation across this small band gap. And these materials are called Dirac semimetals. Now, this linear dispersion has an effect that it protects the electron from having a strong in-medium response. And you can think about this in a way that's similar to quantum field theory reasoning, that the linear dispersion implies a Dirac equation, just like you have in QED. And in QED, you know that gauge invariance protects the photon from getting a mass. So likewise here, the photon being protected from getting a mass implies that optical screening is not so strong. And that dramatically improves the reach of these semi-metal type materials to the reach of an ordinary metal like aluminum in the superconducting phase. So if I compare the reach of a superconducting material to the interaction cross-section as a function of the dark matter mass, you can see that the reach improves by many orders of magnitude for the same exposure. Now, I do want to caution that these Dirac semimetals are just in their infancy in terms of the ability to synthesize them with the characteristics that one would want for a direct detection experiment. Furthermore, I think that we still don't have good techniques for being able to read out an electron excitation created in one of these materials. The point that I want to emphasize here is that details about the material response is very important for selecting the type of target material for a direct detection experiment. So lastly, I'd like to comment briefly. So far, we've been focused on interactions that respond through coupling to charge or to nucleon numbers. So these are spin-independent interactions. Materials also, collective excitations also have spin-dependent interactions. And an example of that is these so-called magnon modes. So there are certain types of light-dark matter particles that will couple predominantly to the spin of the target material. And you can still excite through these interactions, these spin waves. So a classic example of a material with a strong spin wave is yttrium iron garnet. So this is a ferromagnetic material where the iron, you have 4 of these YIG molecules in a single unit cell. And so you have 20 magnetic ions in the unit cell, and each one of these magnetic ions has a magnon branch associated with it. Again, the lightest one is a gapless mode, and then the rest of these are gapped modes. And again, you can compute the effective coupling of these magnon modes to the dark matter. And so that's what's shown here. So here is a spin-dependent dark matter candidate. Again, we're looking at light dark matter going down, in this case, to 10 keV, where stellar cooling bounds start to kick in. And again, if you had sensitivity to dark matter, kilogram year exposure, you could cover this open parameter space that's not currently constrained. I also think that this is quite a far futuristic experiment because we don't currently have a good way of reading out single magnon excitations. This is a harder thing to do than to read out single phonon excitations. So to summarize, in terms of the feasibility of searching for light dark matter with 10 to 100 millieV energy resolution, polar crystals of all the wide range of ideas that I've explored, I think are the one that are most likely to be realized in the near future and are have quite good prospects, both theoretically and experimentally, for being able to detect light dark matter. As I emphasized earlier on, there's an absorption process that allows you to go from the keV scale down to the millieV scale, where the mass energy now is converted into an excitation in the material. So for example, I can have dark matter come in. Let's say it's a dark photon. It has a very small coupling to the standard model. It's not absolutely stable, but it's stable on the lifetime of the universe. For example, I can excite an electron from valence to conduction band, say in a Dirac material, or I can have the dark matter particle be absorbed on one of these inelastic optical phonon modes. And then I can compute the size of this effective coupling to either the electron or the ion charge, for example, if this is a dark photon. And you can see that again, with a kilogram year sensitivity, there's a many order of magnitude improvement over, for example, stellar cooling bounds. So again, an example where with very modest exposure, one can cover a very wide range of new parameter space. Now, I think as you probably likely know, there's been a lot of experimental progress in this area in recent years. And there are a number of experimental proposals for small project development and R&D. So for example, this has required multiple efforts of many of us to bring these ideas together and to make the case for the funding agencies to move forward with the funding experiments in this area. And this has just now started to happen. The Sensei experiment, for example, is funded, and a polar material experiment called the sub-EV polar interaction cryogenic experiment has also been funded. And so what you should expect to see in terms of the near and the far term, so if we cut this plot off at GeV, so GeV and above, I'm thinking of as being WIMP type experiments. And the light dark matter now through scattering, again, can cover another 6 orders of magnitude at lighter mass through absorption, but just highlighting for the moment scattering. In the near term, experiments are now reaching MEV mass resolution, generally poor sensitivity to cross section because they're still dealing with backgrounds. But with the amount of mass that they have in those experiments, one hopes to be able to get down to the 10 to the minus 41 to 10 to the minus 42 centimeters squared types cross sections. And then further along, there is currently R&D effort underway to get to 100 millieV energy resolution, which will allow you to get the higher energy optical phonons, single optical phonons in these polar materials like silicon oxide, for example. And that will allow you to push down to around 100 MeV or 100 keV in mass, and likely another order of magnitude then over the coming years as that energy resolution improves. I probably don't need to tell you that now there are many results that are coming online. I did not mean to be discriminatory here because there are now a lot of papers that are publishing results in this 1 MeV to 1 GeV mass window. I would just like to highlight that in comparison to when I first started talking about these light dark matter experiments and pushing to light dark matter mass, which it was all the way in 2008, 2009, I was told that going below keV energy resolution would be extremely hard. And in that decade of time, we've already gotten 3 orders of magnitude in energy resolution improvement, struggling with backgrounds at the moment. So I can imagine that over the next decade that we should be able to further improve that and reach down to, say, the 10 millieV energy resolution scale. Well, you'll really be able to target a lot of the most interesting light dark matter model space. I briefly touched on the fact that there are funded experiments moving forward, and I would like to emphasize that there's a common R&D path. The sensor that's fabricated on the surface of whatever target material that you've chosen can be ported to multiple targets. So for example, if we focus for a moment on a TES readout, and so you fabricate these TESs on the surface of whatever your target material is, you can imagine porting this technology once those sensors, the TES sensors or the MKID sensors or the SNSPD sensors, whatever it may be, to multiple different target materials. So for example, the R&D work that's going on right now, they're not even using a polar crystal. They're using a semiconductor, silicon, but working to improve the energy resolution of these TESs, and then going forward, eventually putting that on a polar material like silicon oxide or like sapphire. As I said, this is now funded by DOE, Tesseract, TES with sub-EV resolution and cryogenic targets, is moving forward in R&D, mostly based in Berkeley. And the sub part of this experiment that focuses on a crystal target is called the SPICE experiment, sub-EV polar interactions cryogenic experiment. So of course, what you all want to know about is backgrounds. Radiogenic backgrounds are not going to be problematic. The solar neutrino background does become important with a kilogram-year exposure. So here's the rate in terms of the number of events per kilogram year. You can see that this peaks around electron volt energy, of course, depending on what the mass of the target nucleus is. Another issue is going to be coherent photon scattering. So you're going to need a really good photon veto. That's all I'm going to say about backgrounds. Here, for expertise on the backgrounds, I would defer to my experimental colleagues like Matt Pyle or Sunil Goala, who specialize in dealing and mitigating with these backgrounds. So one other thing, just as a fun, by the way, discussion, is we of course should always try to keep our eyes open, especially given the unknown nature of the dark matter. And we've been focused in this talk on this light dark matter window so that we could go into a few details on these dark matter candidates. But what about very heavy mass dark matter? So I want you to imagine for a minute that we had a hidden sector, and the hidden sector had a structure like the standard model, but it didn't have a photon. So there was no light force in the hidden sector that would provide a Coulomb barrier. What happens in such a hidden sector? Well, even making such a modest modification to the standard model structure has huge implications for the cosmological history. So let's do a thought experiment. Let's take BBN at 0.1 MeV. That's where BBN happens. The reason that it happens there is due to the deuterium bottleneck, the energetics of the deuterium bottleneck. Now, the way that you compute the size of nuclei is to solve the Boltzmann equation. So that just says the size of the nucleus depends on the rate at which nucleons fuse to create larger nuclei. Now, if you just do a very simple back of the envelope estimate with a cross section, which is typical nuclear cross section, a velocity of the dark matter, its number density at 0.1 MeV, you do this calculation with the Coulomb barrier, like in the standard model, and the number of nuclei, the size of nuclei that comes out is about 10 nucleons. That's remarkably similar to what we know we get from detailed BBN calculations, which is that this number is around, we get lithium-7 in the standard model. However, if you remove the Coulomb barrier, you keep everything else the same. Now instead, you get nuclei which are 10 to the 9. They're huge nuclei. So this is a way to produce very heavy dark matter, super heavy dark matter from very light constituents. So why is that relevant for dark matter experiments with a low threshold? The basic reason is that these large nuclei, or nuggets, as I call them, have a macroscopic, they're quite large. And so therefore, to be able to take advantage of the coherence in the form factor, you want to have a long de Broglie wavelength associated with the momentum transfer. As a result, these light dark matter experiments can have a very strong sensitivity for a very modest amount of exposure. So if you compare, for example, a kilogram year in a semiconductor with an energy resolution of 10 millieV against xenon 1 ton with 98 kilogram years and an energy threshold of 5 keV, you can see that the semiconducting, much smaller semiconducting experiments fare far better. So it's interesting that these experiments that are designed to look for light dark matter instead can have very strong sensitivity to heavy dark matter. So I'm going to conclude. My point of view is that given where we are in the search for dark matter, it's not the time for narrowing the field. We need to think about new types of dark matter detectors, looking beyond nuclear recoils. The target diversity is essential for doing this, and what we're doing is leveraging progress in materials and condensed matter physics to be able to realize these detectors. So I think of this as an iterative process. So we've learned, that the universe is dominated by invisibles. Thanks to Fritz Zwicky and Vera Rubin and others who made all those beautiful measurements. Then we tried what we thought was the most likely set of hypotheses. The WIMP has definitely received the most attention, although the AXION is getting up there. Now we're broadening these experiments to look for general particle-like dark matter or wave-like dark matter. And we'll see how this field evolves. I really think that we need many probes to look across this broad range of astrophysically motivated dark matter candidates. So I will stop there and take questions. Thank you.
Thank you very much, Kathryn, for the very nice talk. Are there any questions for Kathryn? Fabrice, go ahead.
Yeah, hi. So I have a side question. Recently, I was looking at nuclear physics experiment where people look at missing gamma in a couple of gamma experiments. So in the 100 keV to MeV range. Is that of any interest? What do you know much about this? Do you have an opinion about it?
Missing gamma.
So you have you have two gammas in a typical nuclear decay. Somehow it decays through two states, and then you look for 10 to the minus 9 probability that one of these gamma goes to a dark photon.
Right.
And so you look for a missing of this gamma every 10 to the minus 9 or something like that.
Sure. Yeah. So the idea being there that one of the photons could mix to a dark photon and decay it visibly, and then that would provide a probe of hidden sector dark matter.
Yeah, that's right. And now maybe,
Yeah. So my initial response, I mean, I'm sure that people have looked into this and have computed reach curves. I think the question is, oh, what happened here? Something happened here. I think the question from my point of view is how the sensitivity will compare to direct detection. Because if the probability is 1 part in 10 to the 9, that would suggest that the coupling constant needs to be at least 10 to the minus 4.5. Well, a little bit larger because there's space-based suppression. And if I go back to this, plot, this curve here, as I said before, has a effective coupling of this dark photon. So what they're probing here is a decay of this photon to dark matter with an effective coupling constant, which is on the order of 10 to the minus 4. That's what I hear you saying. This curve right here actually corresponds to this effective coupling constant on the order of 10 to the minus 10.
I see, okay.
So in principle, it's actually far more sensitive. Now, on the other hand, this is for a massless dark photon. Now, if the dark photon is massive, then the coupling constants become much bigger. And in that case, the question would become for, for a dark photon that could be probed with mass, what did you say, 100 keV?
Yeah.
So the issue with 100 keV massless particle with a coupling constant of 10 to the minus 4 is that those can be produced in like supernovae. They would, if the coupling constant were that big, typically, would be in conflict with, supernova cooling bounds, for example. So, so just, talking about this very informally right now, it would seem to me that there are other types of experiments that would have better sensitivity. That said, it's possible that there would be a window that would be consistent with all the bounds and could still be observed. It would be a detailed question at that point.
Right, excellent, thank you. And thank you for a great talk.
So are there any other questions for Kathryn? If not, I would like to thank Kathryn again. And okay, and I will wait for the slide at some point.
Okay,
if you can.
Sure.
Thank you very much again, and have a good day, everybody. Thank you. Bye-bye.
Thank you.
Yep. Thanks again for the talk.
Thank you. Bye.